Hello everyone, welcome to the online course on digital logic design, and the topic of today's lecture is combinational circuits. So let's start with the basic definition of a combinational circuit. A combinational circuit is a digital circuit that is composed of logic gates whose outputs at any instance of time are determined directly from the present combination of inputs without regards to previous input. It means that at any instance of time, the output of a combinational circuit are only a function of present input at that instance of time. Outputs are not dependent on some previous inputs or some previous outputs. A combinational circuit consists of input variables, logic gates, and output variable. So basically there are three things that completely characterize a combinational circuit, and those are input variable, the Boolean expression or the Boolean function which expresses a relationship between the input and the outputs, and then the output variable. The logic gates inside a combinational circuit accept signals from the inputs and generate the output based on the Boolean function that for which they are used to implement. So this is a general structure of a combinational circuit. We have n input variables and m output variable. So n input binary variables, they receive information coming from the external source, and since there are n possible input variables, so the total number of possible input combination is 2 raised to power n. Every combination is a binary combination of input, and each output corresponds to one Boolean expression. Each output corresponds to one Boolean function. So if there are m output variables, then it means that there are m Boolean functions, and each function is of n variable. How to design the combinational circuits? The design procedure starts with the description of problem. The problem is stated. In the next step, the number of input variables and required output variables is determined. After that, the input variables are as well as the output variables are assigned letters from English alphabet, and then the truth table is derived. What is the truth table? It is basically a table between inputs and outputs. So if there are n inputs, then it has n input columns, and if there are m outputs, then it has m output column, and the total number of rows in truth table is equal to 2 raised to power n, and each row corresponds to a unique input binary combination, usually starting from 0 0 0 up to all ones. So it is a kind of brute force approach in which we list all possible binary combinations at the input of a combinational gate, and for each binary combination the corresponding value of output variable is listed over here. If it is 1, then 1 is written, else if it is 0, then 0 is written. From the truth table, the simplified Boolean expression for each output column is obtained. For example, here if we have 3 input variables, and 3 output variables x, y, z, and the inputs are a, b, c. So there would be 3 Boolean expressions for this circuit, one for x, one for y, and one for z, and each Boolean expression would be a function of variables a, b, and c. And these Boolean expressions are obtained in a simplified form using K-maps or Boolean algebra. We have discussed already a number of examples for Boolean function simplifications for both K-maps and Boolean algebra. And finally, the logic diagram is constructed, which consists of logic gates. There are a number of combinational circuits which are used in almost all present digital systems. They include adder subtractors, multipliers, multiplexers, demultiplexers, encoder decoders, code converters, parity generators, comparators, shifters, read-only memories, programmable logic arrays, and programmable array logic. So in the upcoming lectures we will discuss a number of combinational circuits, and we will discuss their functionality and their architecture. So let's start with the simple example. Example 1 is a parity generator. What is the function of parity generator? Basically, a parity generator has got n inputs and 1 output, and it makes sure that the number of ones in the input combination is either even or odd. So if it is an odd parity generator, it will ensure that the number of ones present in the input combination is odd. So if the number of one in the present is even, then it will output a binary 1 to make it odd, and if the number of 1 is odd, then the output P would be equal to 0. After the functionality of this circuit is stated, the next step is to construct its truth table. So this is a truth table. Let's assume a 4-bit parity generator which has 4 inputs D0, D1, D2, D3 and 1 output P. And since there are 4 inputs, we have 16 possible input combinations starting from 0, 0, 0, 0 up to 1, 1, 1, 1. Now for each input combination, we will see that either the number of ones in the input is even or odd. If the number of ones in the input combination is even, then the output P is equal to 1 to make it odd. Similarly, if the number of ones in the input combination is odd, then the output P is 0. So in this way we will list the value of output variable for each possible input combination, and this will make our truth table. In the next step, we will highlight the rows where the value of P is equal to 1. So here we have 8 possible rows where P is equal to 1, and we will construct a K-map which would be 4 variable K-map because there are 4 input variables. So D0, D1, D2, D3. D0, D1 would map along the rows, and D2, D3 would be mapped along the column. And here in the mapping we will having gray encoding. This is what we have already discussed. So for each row where the output variable P equal to 1, we will mark a 1 over here, and since there are 8 rows where p is equal to 1, there would be 8 boxes highlighted where p is equal to 1, and each box would be corresponding to the corresponding min term of input combination. For example, in the first row we have D0, D1, D2, D3, all of them are equal to 0, so the min term corresponding to this box is equal to D0 complement, D1 complement, D2 complement and D3 complement. Similarly, for this box here we have D2 and D3, both of them are equal to 1, whereas D0 and D1 are equal to 0, so the corresponding min term is equal to D0 complement, D1 complement, D2 and D3. In this way we will list all the min terms of highlighted boxes, and from the K-map we can see that these boxes cannot be grouped together in any forms. All of them are separated, so there would be a total of 8 min terms, and each min term would be a 4 variable min term, and this is what we get in the Boolean expression that comes from the K-map. Now we see that this is a classical example where K-map fails to provide us most optimal simplification. So we will see that if we can apply some rules of Boolean algebra to simplify this expression further, and from here if you see, if we take a complement, b complement variables common from these two terms, a complement b common from these two terms, a b common from these two terms, and a b complement common from these two terms, and so we come up with this Boolean expression. And from here you can see that this term c complement d complement plus cd, this is nothing but an XNOR function, and XNOR function is an XOR function with a inverter at the output. So a XNOR b equal to a complement b complement plus ab. So if we compare this with this, we see that this is basically an XNOR function of c and d. Similarly, this term is basically an XOR function of cd. This is XNOR of cd and this is XOR of cd. So if we continue to simplify it further in these steps, we come up with this Boolean expression, which is a XOR b XOR c XOR d whole complement. And you see that if we compare this with this term, this will have a large number of inverters, AND gate and OR gate, so its schematic would be complex. But if we implement this expression using Boolean gates, we come up with this simplified schematic, which only consists of 3 gates. 2 of them are XOR gate and 1 of them is XNOR gate. So from here you can see that simplification of Boolean expression provides us with an advantage of saving the number of logical gates to implement a combinational circuit, and this in turn translates into area saving, cost saving and saving of power consumption of the Boolean combinational circuit. So this concludes our first example. In the next few lectures we will see some more examples of combinational circuits. We'll see you in the next video.